So Teemu, we're looking forward to hearing what you have to say.
Thank you very much, Andrew and everyone present for joining this celebration. I'm forever grateful for, well, most of the same reasons as everyone else has been here saying, how Andrew has been so kind and supportive. And I would have never realized that I'm feeling a little bit less special now in this sense, because I see that there's 150 people to whom he has been equally supported, but I don't feel too bad. But anyway, a very special moment as well here, and congrats, Andrew, of course. So the topic, which will touch on the work that we did with Andrew and his other nice piece of work along these lines. And this is also very much related to what Tara was just speaking of in terms of the sequential prediction and regret and so on, as you will see. I should point out that this work, let me see if I can operate this. So Elias Jääsaari is currently my PhD student. He did this, I can say he basically did this work in his master's thesis, which was kind of, quite unexpected that he'd be able to do all this work, supported by some other Finns and colleagues in Helsinki and elsewhere. Right, so we'll be speaking of MDL, universal prediction, universal compression, and model selection. So just to get us straight on what I mean by various things, usually, or the usual sequence X, N symbols and N symbols, and we're talking about a finite alphabet of size M here, and at some point we're going to make M really large, as you could have guessed from the title. And what we're going to do is look at log laws prediction. Meir gave a nice talk about universal prediction yesterday and basically set the scene already, but just maybe to refresh, we're predicting the k plus 1th symbol based on the first k symbols, and if you just add up those logarithmic losses, you get the minus log probability as the loss, or indeed the code length if you were to compress that block of data, ignoring integer constraints. What drew me to look into these problems was, as Andrew mentioned, Jorma Rissanen, who was very influential, obviously, in the information theory community and myself. So we'll use this code length for our data as a criterion for model selection. So if we try different models for which these probabilities will be different, we'd probably be choosing the one for which this quantity is the smallest. Okay, so that's the basic setup, and we'll be working within this framework. So in the sort of more recent versions of MDL, you'd be usually trying to minimize the regret. So by regret, we mean a scenario where we have a class of models, perhaps parameterized by some parameter theta, and we are to choose a distribution Q to represent that class, or let's say compete against that reference class as good as possible. And we measure how well we've succeeded in that by looking at how much longer code length Q assigns to the sequence xn compared to the best model in this reference class. So we'll be minimizing the code lengths or maximizing the log probabilities within the class, and then since we're always going to we're never going to be able to beat the best model in the model class for all sequences, we're trying to minimize how much we lose to the best model, so how much we regret in that way the use of the model Q. And as shown here, the model Q doesn't have to be within the class, so that's one thing to note. And if we were really clever, we'd probably choose the model that has the worst, the smallest possible worst case regret. And notice this is the pointwise or the individual sequence case where we don't assume that the data is generated by any of these models. We'll simply be looking at the worst case individual sequence. So that's kind of a simple and neat and nice, as at least I think so. And the solution in many classes is known for this problem, the Minimax problem, and it's known to be the normalized maximum likelihood distribution as shown by Sharkov. And just to sort of simplify the notation and the scenarios, we'll be now focusing from here on the multinomial case, where our sequence is just, again, discrete symbols, each appearing with probability theta, and then theta I, let's say, or theta xi. So that's the ith symbol in the sequence. So the NML distribution, just you maximize the probability for each sequence, and since these alone would not make a distribution, they'd be summing up to more than one, you just normalize that, and hence it's quite appropriately named the normalized maximum likelihood. Okay. There's a few drawbacks, and we've actually looked with Andrew into some of them, and one of them is that this is not always very easy to compute. Well, I should also mention that it's not always defined, as for some model classes, the normalizer would be infinite, and these model classes can be either discrete or continuous, so the data can be discrete or continuous. And Andrew has a bunch of nice pieces of work related to that problem as well. We were at some point looking at the problem of computing sequential probabilities, by which I mean the probabilities where we're looking at sequences, let's say initial sequences before the nth, sort of the horizon n, which is the length of the overall sequence here, is reached. So why there's a difference between initial sequences and the full sequence is that the normalized maximum likelihood distribution will assign different probabilities to, let's say, the first 5 symbols, depending on n. So if you choose n to be 100 or 200 or indeed 5, you would get a different prediction for the first 5 symbols, which is a little bit odd, but that's the way it comes out from the Minimax problem. So again, if we have a horizon set at 100, so n equals 100, it might be really difficult to compute the distribution of let's say, the first 5 symbols. And you would need those in order to, let's say, sequentially compress your data without having to work on these whole blocks at a time.
Or even to predict with this original motivation.
Right. Either compression or prediction, as far as I'm concerned, they're just the same problem. So I kind of forget to mention the other now and then. Okay. So if we were to look for some solutions to this, let's say the computational problem of being able to predict the sequential probabilities, Bayes mixtures or mixture distributions, I'll call them Bayes mixtures because of their frequent use in the Bayesian framework, they're a very promising approach. Because such things where you have, let's say, a simple, usually IID likelihood part multiplied by the prior and then integrating out the prior, they're very easy to handle, especially if you use so-called conjugate priors as the prior. And they also have sort of certain theoretical properties that they're admissible and so on. So they're also sort of probably good, usually sort of you can get good predictive distributions from such constructions. But the NML itself is not constructed in this fashion, and thereby you'd maybe want to look at the relationship between mixture codes and NML type codes. And here I'll sort of plug in sort of the work that we did with Andrew, where we actually wanted to represent, and this was for the Bernoulli case, or at least the multinomial case in principle, we wanted to sort of try and represent NML. So this is the joint probability assigned by the NML distribution to the sequence literally as a mixture of the type of the Bayesian or the mixture type. And we were able to show that it's kind of a very straightforward proof that if you choose any n+1 point masses or points in your parameter space, in the Bernoulli case it's from 0 to 1, and weight them appropriately, then you'll get exactly the NML distribution. So it's not an approximation, but it's an exact representation. And the curious thing, which I found very sort of somehow like thought-provoking or curious, is that sometimes these weights can be negative. And of course, they will eventually have to, or overall, they have to sum to 1, because otherwise the mixture of these distributions would not turn out to be a mixture. But sometimes you get, the ones in the front row might actually see that the scale of these weights here is 4 to the, or 10 to the power 7. So it's 10 million. So if these were interpreted, and don't start throwing objects at me, if these were interpreted as probabilities, we would have probabilities equal to 10 million. Or, even better, minus 10 million. So if there's any probability theorists here, just apologize for what I just said. But so it may be better to think of them just as weights or signed. Well, it's a signed weights, but I said, signed distributions. I forgot what term we used back in the day. But okay, so that's not really what I wanted to talk about. What I wanted to talk about is another approach to the problem where we're not going to require that we do exact NML as a mixture, but we do something that is asymptotically minimax. And this has been looked by a number of people, as I'll mention in a minute. So what we did is we wanted to sort of, we are as Jorma Rissanen used to say, I'm a simple man. We also wanted to sort of do it simple, and we wanted to just use the Dirichlet distribution as the prior. There are more complicated and complex constructions around, but we wanted to see how simple it can be. So we wanted to ask what are the hyperparameters of the Dirichlet prior that would be optimal in this setting. And we narrowed it down by symmetry arguments to a case where you have Dirichlet alpha, 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 alpha. So as many symbols as you have, as many alphas you'd have to put there as the prior. So it kind of doesn't make sense for in a generic setting to say that, okay, well, this symbol has higher prior probability than another symbol because they're just symbols, right? You don't have any interpretation and meaning to them at this point. So the question becomes, how high should alpha be? And if you've looked into this type of problems, you'd know that, let's say, if you let alpha equal 1, you will have a uniform prior, and this was sort of basically proposed by Laplace, obviously for different purposes, way back, but that's the so-called Laplace rule, the rule of succession. So you basically...
I would say the purposes weren't different. He was doing the sequential prediction for the Bernoulli trials.
Indeed, yes. I was thinking he wasn't doing compression or model selection, but prediction, yes. I think somebody said they're the same problem. Yeah, that's a fair point. So he was using doing the same as we are, and he came to the conclusion that this might be a good choice, and it sort of corresponds to using the uniform prior, which is not, well, out of the question. And then a century, 2 centuries later, just about, Khrushchevsky and Trofimov looked at it from a Minimax point of view, and they were able to show that alpha equals half is a reasonable choice. It has certain properties, and it's even minimax as long as your sequence doesn't come from doesn't have any symbols missing altogether. So it's not at the boundary of the parameter simplex. So that's again a popular choice, and it can be sort of, especially from information theory point of view, very well justified in many cases. Then at some point we've shown that you can use alpha just smaller than 1/2. Asymptotically, it's going to be 1/2, but before you are at infinity, you should use just a little bit less than 1/2, and this can be shown to be asymptotically minimax. So it's a very sort of simple. That's very, very simple, convenient way. Doesn't mean any sort of extra components in the mixture It's just the Dirichlet as such, and that turns out to be minimax, asymptotically. And this was done by Kazuho, Watanabe, and I in 2015. Oops, almost skipped some part where we have a bunch of references to Andrew's work. So just wanted to mention that before this, there was work by Xi and Barron, where there was a construction of a prior with a prior with some point masses or some sort of extra mass at the boundaries of the parameter space and the vertices of the simplex. And then I suppose a somewhat improved construction, 2 decades after that, which I will mention and show in terms of an example in a bit. Okay. So how we differed from this line of work. So now I'm sort of really getting to the work that I'm presenting here, that Elias, my student, did at some point, is that we're looking at m really large compared to n. So this sort of became a thing at some point when Alan Orlitsky and Prasad Santanam looked into these scenarios where you have, for instance, m growing at a faster rate than n. And we even have sort of practical applications in graphical model structure learning where you can have an exponential number of model structures to choose from. Oops, I'm a little bit trigger happy here, but here. So what we did, and this is now 2018, so it's not as fresh as Tara's work, but I think it's still correct. We can show that if m is greater than 2.5 times n, and a little constant, which, there's a number, we can give that. So it's not like, it's not a big number, not 500. Then it's best to use, and this was a real surprise to me, it's 1/3. It's not like 1/2 minus log of something and blah, blah, blah. It's 1/3. It's exactly 1/3. Every time m is bigger than that, this is the best alpha for any Dirichlet prior. And so that's I like this neat thing, even if I say myself. And I can say because it's Elias's work, really. And he figured it out.
So then if it's n less than this, the optimal alpha will be n.
Yeah, if m is less than that, then I don't know what is the optimal alpha. I mean, we can figure it out. It's not really difficult to optimize it, but I don't have a formula in that case. Yeah. But any m bigger than that, that's the exact optimal alpha. Yes, Janis? Minimax optimal, yes. Yeah. The worst case regret is minimized. So for the worst sequence, you look for the worst sequence for any alpha and look at the regret of that sequence. And for alpha, that worst case regret is the smallest. What is the minimax regret? I'll show that in a bit. Yeah. Yeah, Peter.
Do you know that alpha equal to a third breaks down if it's m increases slower than this here, or?
Alpha. Well, I think there's two things. Like so we can show that any m bigger than that, no matter what n is. If n is 1 or more, I don't know what n is less than that would be. So that maybe that's something. Maybe we can look at negative sample sizes. I mean, that's the next paper, right? But anyway, so that in that case, alpha 1/3 is the optimal Dirichlet prior, but it doesn't show necessarily that it's minimax optimal because there could be other priors that could be better in that sense. But if I'll show in a bit that if m grows slower than n, this is asymptotically minimax. So that's kind of two things. It's optimal among Dirichlet, but it's also optimal among any distribution asymptotically. Okay. Yeah, and so the proof idea is actually quite simple. The devil is in the detail, as usual. So this would be, so you're looking at a chart with different alpha values. So this is what you'd be choosing. To choose the alpha, you can choose 1/3, which is the red line here. You can choose, I don't know, 1/2. That's the Khrushchev-Trofimov. I'm not even showing the value alpha equals 1. It would be like off the chart, literally. or it is off the chart. So depending on that, you have different regrets for different sequences. So the different sequences are the different lines here. Each sequence is one line here, because if you have a sequence, let's say this sequence here, then depending on the alpha, the regret is either bigger or smaller. And we can show that there is a sequence whose regret is increasing if you're above the 2.5 times n mark. And if I recall, this is a curious sequence, you wouldn't guess it. It's a sequence where every symbol occurs 2 times. Every symbol that occurs at least once occurs actually 2 times, except if the length is odd, then there's one symbol that occurs once. Go figure. I don't remember why that is, or if there's like I don't know if you can answer why in mathematics, but that's how it is. And then there's a sequence whose regret is decreasing when every time m is bigger than n. And if I recall, and it kind of makes sense, this is a sequence where all the symbols are different. So then it is just better to try and be as uniform and not follow what you've seen so far, because anything that you've seen is not going to appear. So it's kind of this like reverse inductive inference, if you will. So being a really stubborn person who says everything is always uniform, no matter what you've seen until now, is optimal for that sequence. And we can show that at alpha equals 3, 1/3, these sequences have the highest regret, and they also have the same regret. And by that argument, we can say that 1/3 is the optimal regret. Because if you go above, then this sequence will have a bit higher regret, and others too. And if you go below, then that sequence will have a higher regret. But this is the idea in the proof. So there's basically 2 cases. You have to figure out these regrets and see where they are equal, and then show that there are no other sequences for what at that point it is higher. So that's how it works. And then we can show that if you look at the asymptotics, if n grows slower than m, then you get this formula. And that actually, the first term is from Orlitsky-Santanam, already 2004. They show that this is in this case, the asymptotics. And then this next term is from Wojciech Spankowski and Marcelo Weinberger's paper in 2012. And they have the exact same asymptotics. And they were studying NML. So you can see that if NML has the same regret as our model, then we're minimax optimal, because NML does that asymptotically. Yes. So that's the conclusion. This 1/3 is a minimax optimal in this large alpha, so-called large alphabet framework. Yeah. Oh, and somebody asked, what is the regret? So that's the regret. That's the regret of this particular model, exactly. So that's not approximation, that's exact regret. Yeah, I think Jannis was interested in that. So there you are. And if you look, this is the last thing that I'm going to show. Some pictures. Pictures are nice. These are some models. Some sort of potential universal models. I won't say universal models because some of them don't have a vanishing regret. For instance, the 1/2 distribution, or this Krzyzewski-Trofimov thing, its regret grows asymptotically without bound. So it's not asymptotically minimax in that sense. Depending on the definition. I think Mayer said that if the regret divided by the sequence length goes to 0, then it's universal. So in that sense, this model is universal too, because it grows slower than n. But this is in terms of m. But anyway, so the same holds there with n. Okay, my watch says that I have reached my activity level requirement today. So maybe I'll still go on for a few minutes. 1 minute. Okay, thank you. You can optimize, as I said, you can easily optimize this alpha because you know the worst case sequences, the potential worst case sequences, so you can actually numerically optimize it and Bayes optimized. That's this orange thing here, which is kind of very, very low. And then our method is this like, I don't know, magenta thing that has this funky kink here, which I don't know where it comes from. But anyway, so that's just showing that compared to some other choices, it's doing well. Oh, and there's another reference to this Young and Barron work with the tilted, what was it called? Tilted Stirling ratio distribution. That in this case, for a relatively small n, is not as good. But then if you increase sample size to 1,000, then it's actually very, very good. So of course, I didn't want to show anything there where Andrew's work is not shining. So in this case, it is outstanding as always.
Sorry, what's the explanation? This could be better than Bayes optimized.
Bayes optimized is the alpha chosen by numerical optimization. And we know that it's going to be after this point where m is 2.5 times n. We know from the theorem that then you don't really have to do the numerical optimization. You know 1/3 is optimal. But if you're not there, then some other alpha is going to be slightly better.
Yeah, but I said Young and Barron is better than Bayes.
Yeah, it's not Dirichlet. Yeah, so it's in a larger class. So that's why he still beats us.
Not for really big M.
Yeah. So thank you very much.
Any other comments or questions? You know, the starting spirit is the minimum description length principle, which is really a principle of adaptation. Change your mind based on what the data show you. If you saw data where so far every observation was different, or you saw that those that occur precisely twice so far, wouldn't you be led to go down those blue curves to the lower points and use different alphas? You would no longer be minimax for the problem. You know, you wanted to be minimax here for this theorem, but wouldn't you really be doing better individually if you learned from the sequence so far? I mean, the data could fool you. What comes next could mess you up. It's just a general, I'm not expecting you to know exactly where this goes.
How to optimize alpha as you go. That is a very interesting...
It's really a comment for all of us. Minimax is fun, but there's always something a little better to be able to do individually what's right. And the spirit of the method could suggest.
I'm afraid because the game is played so that there's going to be the worst case sequence. So if you'd actually come up with a scheme where you optimize alpha halfway through, then of course your adversary would actually sort of say, ha, Andrew, now you think you were being clever, but I'm going to sort of change right after you
That's
did that,
the worry.
Right?
All right.
So,
Thank you very much. Nice.
It's
He beat me. Okay.